Hi students. In this lecture, I am going to discuss problems based on pressure and force. Let us see first one. Let's see the question given. A solid hemisphere of radius r is made to just sink inside a liquid of density rho with its base horizontal and inside the liquid. Find force by liquid on the base, force by the liquid on the curved surface, the net force by the liquid on the hemisphere. So here we have to neglect pressure of atmosphere. So given solid hemisphere, just sink. Okay. Let us see how to start. Right. First of all, see the condition given. It is a hemisphere. Hemisphere. It is now inside liquid. Condition given that it is just made to sink. So just inside. This is now completely liquid. And condition is the base is inside. Base is inside. Right. Now you can see the first question is force by liquid on the base. So it is very simple and direct one. Here we have to neglect atmospheric pressure. So depth will be equal to R. At a depth R, pressure equal to it is equal to H rho G. H rho G. This is the pressure into the corresponding area. So area of the base, that is a pi r square. It is pi r square. So we have taken now at a depth R, what is pressure? That is H rho G into area. That gives us a force. This is now force. Force on the base. Okay. Direct one. Next focus. The force by the liquid on the curved surface. You can see on curved part. It's the liquid which is above the curved part. Its weight will act on the curved part. You can see here. Focus this part of the liquid. You can see weight of this liquid. Weight of this liquid is acting on the curved part of the hemisphere. Okay. So now we have to focus weight of this part of the liquid. And you can see this is now one cylinder. Cylinder of radius R, height equal to R. Therefore, its volume equal to pi r square into R. This is volume of that cylinder. From that subtract now volume of hemisphere. That is 2 by 3 pi r cube. So this gives us volume of the liquid present in this part of the volume. Okay. That volume into density of liquid. That gives mass of the liquid present in that volume into G. This is weight of the liquid present in that volume its weight is acting on the curved part of the cylinder, sorry, curved part of the hemisphere. Okay, this is a force acting on the curved part of the sphere. Now he's asking net force by the liquid on the hemisphere. So net force by the liquid. So by liquid force acting on the base, this is a value. By liquid force acting on curved part, this is a value. Now this is upwards on the base. It is upwards, and on curved part it is downwards. So net value, force by liquid, net value is equal to force on the base minus force on the curved part. See how much it is. This is pi r cube. This is a pi r cube into 2 by 3. Remaining is 1 by 3. Okay, this is 1 by 3. This is now so pi r cube. You can see pi r square into r, pi r cube into rho g minus 1 by 3 pi r cube into rho g. So net force acting by the liquid on the hemisphere, that is equal to 2 by 3 pi r cube into rho g. That is 2 by 3 pi r cube into rho g. That is the answer. So it is a very simple and direct question. Let us see next one. Let's see the question given. Water and oil are poured into the two limbs of a U tube containing mercury as shown. This is now mercury, this dark shaded mercury. And on one side, we can see what is given here. Height of water column H1. This is water and this is oil. Given height of oil column 20 centimeter and given density of oil 0.9. We have to determine the height of the water column. Wait. Height of water column H1. That value we have to find out. H2 value is given. That is 20. Right. Let us see how to start. So first of all, make the given diagram. The given diagram is so this is the given diagram, U-shaped tube. And in that you can see mercury at same level in both columns. You can see mercury at same level in both columns. This is mercury. Next, coming to left column, it is given water height H1, which we have to find out. Height H1, so which we have to measure. This is water column H1. Coming to oil column. Coming to oil column, given height H2, that is 20. This is now oil column. And this length given as h2, which is equal to 20. Right. Okay, now see what we have to do. So we have learned that when we're having a liquid inside the liquid at a depth h, pressure equal to P equal to H rho G. See here, this is now free surface. In such a case, at a depth h, at each and every point, so same depth, same liquid, same depth, h value same liquid, rho value same. So this is now free surface. When free surface is a horizontal, in such a case, at same depth in same liquid, pressure will be same. Okay, because G is a constant. Now using this logic in this problem, now focus carefully. We are taking a point just below the interface of water and mercury, just below. Next, coming to here, I am taking now just below the interface of oil and mercury, 1 point. So we have taken out 2 points in same liquid. Both points are in mercury. At the same time, both points are now at same level. We can see that both points are now at same level. So same level in same liquid. Both are in mercury. That means at these 2 points, the pressure must be same. I'm repeating, I have taken both points in mercury only at same level. Therefore, pressure at these 2 points must be same. So since it is now just below mercury, the pressure is now P naught plus H1 rho of water into G. That must be equal to, coming to here, P naught plus H2 density of oil into G. Now P naught gets cancelled. Now condition is H1 density of water is equal to H2 density of oil. Okay. Now just substitute values in that. H1 we want to calculate. Density of water, it is 1 gram per cc. H2 given 20 centimeter. Density of oil, it is given 0.9. That means H1 is equal to 18 centimeter, right? So key point is at same level, same liquid. Then P value same. Okay. And you have to focus free surface is horizontal. That is very important. So answer is 18 centimeter. Let us see next problem. Let's see the question given. Water stands at a depth h behind the vertical face of a dam. Dam is now having vertical face and depth of water is h. It exerts a resultant horizontal force on the dam tending to slide it along its foundation and a torque tending to overturn the dam about the point O. Neglect atmospheric pressure. So condition is water is at a depth h. See diagram for this. This is now the vertical face of the dam and at a depth h you're having up to depth h water is there. Now he is asking calculate horizontal force, torque about to the height at which the resultant force would have to act to produce the same torque. And given here L is length of the dam. Let us see how to start. Let first make the given diagram. Given this is now the dam, water is now up to a depth of h, up to a depth of h. Next, and this is point O. This is a point O. Calculate horizontal force. So horizontal force means, so we can use the result like the entire force acting at its center of mass. So depth will be h by 2. So I'm taking directly that result. Otherwise, we have to use integration at a depth of y. Take a strip dy. Force acting on that rectangle, right? So I'm taking directly that result which we have learned in earlier problems. Horizontal force is equal to h by 2 rho g. That is pressure. Okay. H by 2 rho g into corresponding area. This is h and length given L. So area of that gate will be L into H. It is now L into H directly. Okay. Next. See, next question what is asking. Torque. Torque about O. Torque about O. Then see what we have to do. Let us take at a depth Y. At a depth Y. Take a strip equal to width dy. Okay. So this is now one rectangle whose length equal to L, breadth equal to dy. Okay. At a depth y, pressure equal to y rho g. This is the pressure into area. Area is now L into dy. This gives us a force acting on that rectangle. If you integrate now from 0 to h, then we are going to get this answer. Okay. But now we want to calculate torque. Torque about point O. Okay. About O means you can see that force acting now like this horizontally about point O. So distance will be, it is a h minus y, right? This gives a torque about point O because of this force. It is because of this force. Like this, we have to take torque due to each force on the each rectangle. So now integrate. That is from y equal to 0 to up to h. So this gives us a torque about 0.2 and remain just calculation part. So torque about 0.0 that is equal to, let us take first of all constants outside. Constants rho g l take outside. Rho g l taking outside. Remaining is y dy integration of taking y inside hy minus y square into dy. That is equal to now see calculation part rho gl remaining is h into y dy. H into y square by 2. H into y square by 2 minus y square dy. It is y cube by 3. Okay. Now take limits 0 to h. H and h square, h cube, right? And here also h cube. Take outside rho gl h cube taking outside, remaining is now 1 by 2 minus 1 by 3. That becomes now 1 by 6. This is now torque about point 2. Okay. Now question is the height at which the resultant force would have to act to produce the same torque. Okay. Height means we take from ground. Okay. Means from here. At what height? Suppose that is now. So take it as h dash. At what height this force has to act. Okay. So that because of that force, torque will be the same. Okay. Let us see calculation. So we are taking now this entire horizontal force is acting at one height from the point O, so that it will produce the same torque. That height is how much? Okay. So that a horizontal force Fh into height h dash produces now same torque. Substitute values h by 2 rho g into LH. This is equal to rho GL upon 6 into H cube. See the calculation part. H square, here H cube. Next, rho GL, 2, here 3 times. That means, I think I have missed here H dash it. H dash is missed here, H dash. And what else? H by 3. Right? It is cross check once. H by 2 rho G, right, into LH into H dash. Okay, right. So from this H dash is equal to, it is H by 3. So force must be, this entire force, this entire horizontal force must act at a height H by 3 from point O, so that it will produce same torque. Okay, and that location is known as center of force. That point is known as center of force. That means at which point this entire horizontal force has to act to produce same torque, and that point is known as center of force. This is now center of force. Okay.